Millions of cars, thousands of kilometers covered every day on a network across an entire country. French motorways count among the most advanced of its kind, and 3 of them are absolute benchmarks, with infrastructures beating all records of civil engineering. There's the A40, a dizzying achievement that holds the record for construction work in extreme conditions.
Its viaducts and tunnels are anything but ordinary.
When planned, the Paris Ring Road seemed a crazy adventure. How did its builders manage to cut a swathe through a densely populated metropolis?
It's the busiest road in Europe.
How did they succeed in building a bridge over a marshalling yard in the middle of Paris?
The main span is 160 meters long, so you don't have a support for 160 meters.
The A10 between Paris and Bordeaux is the longest motorway in all of France. 557 kilometers, more than the length of Ireland. A motorway designed to cope with all weather conditions. The A10, the A40, and the Paris Ring Road each are masterpieces of civil engineering. The history of French highways is fairly recent. The first studies on a new kind of highway, intended to speed up overland traffic, go back to 1927. Yet lack of adequate construction techniques and World War II postponed the project for about 20 years.
The first French highway was opened in 1946 between Saint-Cloud and Orgeval, the autoroute of the West.
However, the use of motorways has yet to be learned.
People did U-turns crossing the median, as there were neither guardrails nor any other separations between the lanes. Some would stop on the hard shoulders, get out the camping table and have a picnic.
Motorways are a novelty. Only with the creation of an entire network do people become accustomed to their use. And from the 1950s onward, it extends ever further. Today, there are 142 motorways across the country, totaling 11,000 kilometers. Due to the toll system, they're the most expensive roads in Europe. Yet, when it comes to the quality of their surfaces, safety and cleanliness, they set standards unique in the world. One of them is considered one of the most beautiful emblems of civil engineering. The A40 links the city of Mâcon in Burgundy to Switzerland. It's a succession of great feats, holding the record for engineering structures in an extreme environment, the heart of the Alps.
It's an extraordinary achievement. The A40 is really a three-dimensional motorway. It goes up, it goes down, it crosses mountains and spans valleys. For that you need viaducts and tunnels.
Each of these works is a technical feat, given the number of problems involved.
A mountain massif is an immense challenge for infrastructure designers. Building a motorway high up in anything but favorable conditions is also a most intense human adventure. Yet, there is an increasingly urgent need to facilitate trade between France, Switzerland and Italy. In the early 1950s, the country's economy demands the creation of a new overland route. But the terrain blocks any project for a long time.
The plans have ripened over perhaps 20 years.
Once the project is given the go-ahead, the pace of work is exceptional. However, conditions along the planned route of 208 kilometers are difficult.
My teams had to work even in temperatures of up to minus 20 degrees Celsius, day and night.
The number of works needed to connect France to Switzerland is impressive. No less than 12 viaducts and 4 tunnels. the first of which is a technological feat in itself: the Chamois Tunnel.
It's the longest tunnel on the A40. It runs for 3.3 kilometers under the Chamois Plateau, which rises to about 1,000 meters above sea level.
Yet, before starting work on the tunnel proper, the teams need to know the nature of the rocks they are going to encounter. To that end, they dig an exploratory tunnel 3 meters wide. It will pierce the entire width of the mountain. Once finished, it will be joined on its left by a first tube. Then a second tunnel will be added on its right. The exploratory drills revealed that the plateau consists mostly of limestone, which formed 200 million years ago. It's an advantage, as limestone is extremely stable. Yet it's also particularly dense. How do you pierce it? The solution is provided by an exceptional machine.
It was a real technological revolution at the time. We had RoboFour-type tools that were entirely computerized. They would arrive and take up their positions with their sets of 4 arms, which all drilled at the same time. And progress was then displayed to us on computer screens.
The RoboFour allows 165 holes to be placed with extreme precision, which will then be filled with explosives.
We then inserted detonators with a micro delay. The idea was to cause a sort of chain reaction to blow up a maximum mass of stone.
The 30-millisecond delay between the different explosions causes a much more efficient detachment of the rock than if all fuses had exploded at the same time. Thanks to its onboard computer, the RoboFour digs with great precision down to the last centimeter, resulting in a perfectly regular pattern in the wall.
Then we clear the section of rubble.
Astronomical quantities of rock need to be evacuated. Enter the dumpers, American-built monsters of transport.
They're not like the trucks you see every day. They're really big.
Thanks to the efficient placing of the explosives and speedy recovery of the rocks, the drilling of the tunnels, begun in 1978, is completed 6 years later. Next, it's necessary to provide the tunnel with lungs. 2 ventilation sites are thus built at each end. Giant fans suck out exhaust emissions while permanently injecting clean air.
There are 3 ducts in the tunnel ceiling, a central one for the extraction of smoke and stale air, and 2 ducts on the sides for the supply of fresh air.
In 1986, the Chamois Tunnel consists of only a single tube. The second tunnel, parallel to it, wasn't added until a decade later.
In the first tunnel, both directions of traffic passed through the same tube. Only 10 years later, when they dug the second tunnel, did it become possible to provide one-way traffic in each tube.
That's why today, the speed may surprise drivers in here. 110 kilometers per hour in a tunnel is not common. In the Mont Blanc tunnel, it's limited to 70 kilometers per hour. It's not the only surprise for motorists and truck drivers. At the exit of the tunnel, they are confronted with a disconcerting experience. The motorway seems to be taking off.
You come out at the edge of a cliff.
The tunnel leads directly onto one of the most impressive structures ever built in France, the Nantua viaduct, 80 meters above ground.
There was a big worry when the tunnel opened. Some truckers coming out of it were overcome with vertigo. No kidding. They abandoned their trucks on the road and left on foot.
The Colossus of concrete extends over 1 kilometre with a deck of 11,000 square metres. 10 piers support it, the highest rising up to 77 metres, the equivalent of a 30-storey building. The piers required the pouring of 5,000 cubic metres of concrete. It was one of the most complicated construction phases, as the environment in the Nantua Valley is infernally complex.
It's a very difficult area from a geological point of view. Everything moves.
This problem is inherent to civil engineering in mountainous areas. To avoid any risk, it's necessary to have piers that can resist the hazards of the environment, and to that end, they must be deeply anchored in the ground. The prerequisite for this is particularly deep foundations.
You need a stable base.
Shafts of 5 meters in diameter are then excavated. They can exceed 20 meters in depth until they come to rest on solid rock formations of foolproof stability. Then they're filled with concrete and covered by a shield. On colossal bases of 250 cubic meters of concrete, the workers can thus raise the actual piers at a rate of 2 sections of 4.5 meters per week. Inside, there is a void to keep the pier from being too rigid. It must be able to absorb the movements of the deck during violent gales and not overstretch its supports. The risk is especially high at the first pier.
The underground at this site consists of extremely unstable scree. It's impossible to use any scaffolding.
A hand-dug exploratory shaft 20 meters deep rules out any conventional solution. The shifting scree is a real problem, whereas the other 9 piers of the 1,000-meter deck are perfect.
You still have one end to do, which is called the abutment. So the question is, how do I build that part?
The answer is a first in France. A counterweight in the tunnel. It's an unprecedented concept to compensate for the absence of the final pier.
We would dig a huge cavern, a real cathedral, something 18 meters high, 10 meters wide, and 30 meters deep, inside the cliff.
Positioned just below the tunnel, the block of concrete will support the weight of the last span of the deck, which is considerably longer than the others, 124 meters, more than a soccer stadium. Once the 9 piers are erected and the counterweight is in position, gigantic cranes, more than 100 meters high, move in the 290 blocks that form the final deck. It's made up of 10,000 tons of concrete. But there are also more than 1,500 tons of steel inside, which poses problems of its own.
Since the viaduct is high above the ground, there is an air current on top and below the lanes. And as they're full of metal structures, the cooling is faster and the risk of icing is greater.
That's why this portion of the motorway requires special attention and constant salting during sub-zero periods. Yet the changing temperatures in the mountains could have caused much bigger problems for the entire viaduct.
One of the great advantages of reinforced concrete is that steel and concrete have the same coefficient of expansion. Not many people know that, but if the two materials had different coefficients, it would have been impossible to use them.
The viaduct shrinks in low temperatures and expands in the summer heat. So its length can vary by dozens of centimeters over the year. In 1986, the viaduct was inaugurated with only one lane. In 1996, when the Chamois tunnel got its second tube, an additional lane was added. It's an impressive example of how civil engineering can overcome a tricky series of difficulties and achieve a formidable end result.
The Chinese, who back then were far from building anything like it, visited the construction site extensively, as did the whole world.
And the visitors did not stop there, since there are other spectacular sites on the A40, like the viaduct of Silong. Less spectacular than its Nantua counterpart, it's nevertheless exceptional. The way it hugs the mountain required all the engineering expertise of its time, since here too, the terrain poses truly mountainous problems.
The whole upper part of the area is gravel scree, which permanently slides down to the lake.
It's extremely dangerous ground when having to move equipment weighing dozens of tons. Erecting cranes where they would be most needed is simply out of the question, as the ground could give way if the loads were too heavy. So, how to implement what seemed impossible to many experts? How to create solid supports for each of the piers along the viaduct?
The foundations were a feat in themselves.
They required exceptional ingenuity and adaptation of the geological features. Placing the supports of the future motorway begins.
Each foundation is a huge well, 4 meters in diameter, until solid rock is reached.
Depending on the terrain, the wells can go down from 6 to 35 meters. Digging in scree calls for exceptional precautions. The engineers create a unique mechanism.
We had machines with cylinders arranged in a star shape that would press against the sides, so that the entire contraption was suspended and could dig below it.
A miniature excavator fills metal buckets that are lifted by a winch attached to the Moroccan well, a process that is effective as it ensures the safety of workers on the ground. The Moroccan well thus covers a layer of scree of several dozen meters. To prevent any sliding of the rocks, a ring of concrete 6 meters in diameter is added. This shell is then attached to the solid rock of the mountain by a kind of metallic braid.
Those steel cables are put under several tons of tension.
By anchoring the head of the well, the impact of any movements of the ground is lessened. Structures that have to resist the pressure of thousands of tons sliding towards them are an exceptional challenge for civil engineering. Yet the groundwork apart, there's another decisive innovation, and it concerns the deck of the viaduct.
The designers opted for a light structure.
Due to a reduction in mass, the piers exert less pressure on their supports and on the foundations.
We're in active scree, so it's all about reducing the effect on the substrata.
Yet which elements can be spared without endangering the structure?
The idea was basically saying, we're going to hollow out the thing along the sides.
Dispensing with tons of concrete by designing a new structure would considerably reduce the overall weight. It's the brainchild of French engineer Pierre Richard. He plans to lighten the parts of the viaduct that have to take the pressure of the deck's weight.
His idea was to say, I'm only going to use concrete at specific points. I'll put diagonals where compression and tractions occur, and everything else is useless, so it can be left void.
The result is a spectacular lace of concrete all along the 1,266 meters of the section along the lake of Silong.
That way, we saved 30% of mass, which is enormous, a real technological feat.
It's a world first. In 1989, the Silong viaduct and its lattice work are acclaimed the world over. Yet only one other structure with these specific crosses is ever realized, in Saudi Arabia. The construction technique is simply too complex, as apart from concrete, there are dozens of cables stretched within the viaduct. Since the cables are not protected from rain, frost or wind, corrosion may eat away at the material and weaken the viaduct. Sensors are put in place to detect any brittleness of the cables. The Silong viaduct is regularly checked, inside, but also further up. As the massif above lives, breathes, and at times releases dangerous landslides. So, as early as the construction of the viaduct, cliff motion detectors are implanted.
These sensors continuously record the movements of the mountain and alert us of any potential cracks.
To avoid disaster, additional precautionary measures have been added. It's demanding work, even for experienced mountaineers.
We have to clear the brush at the top of the cliff and then provide secure access to the edge. There are handrails everywhere, yet we have to work hanging on our ropes. It's a tricky job.
Their task is to nail the fragile mass of rocks to the more massive layers several meters inside the mountain. It's done by inserting rods 8 meters long and weighing 80 kilograms each. A machine helps to drill the rock. The compressed air device is moved every 2 meters by helicopter to allow the operators to perfectly square the sensitive surface. The rod is driven into the hard rock. Then cement grout is injected to seal it.
Once the grout overflows, the injection has worked.
All the while, during these operations, the rock is covered by a net, as conditions are delicate.
When faced with nature, you have to remain a bit humble, as we don't really know in what state the overhang is, if it's close to falling, or if it will hold.
A fence at the bottom of the cliffs is intended to retain or slow down any falling rocks. Drilling in a fragile mass compels the installation of yet another sensor. If the cliff shows signs of violent movement, it sends an immediate signal which activates the instant closing of the motorway. When the A40 was inaugurated in 1990, after 17 years of work, not all these safety measures had been implanted yet. Anyway, it had been an outstanding effort. The then President of the Republic, François Mitterrand, called it the Motorway of Titans.
Delegations came from Northern Europe, from Japan, I think even from Australia and the United States. It's proof that people were indeed interested in this site because of the density of works along the route.
The A40 holds the record for exceptional engineering structures along its 208 kilometers. It's a showcase of civil engineering,